Hello everyone, welcome back to the latest lecture session. I believe we looked at mass balance in the previous couple of sessions, and I believe we digressed, or rather we wanted to look at mass balance in detail before moving on to some of the applications. But obviously in this class we are only going to look at few applications or minor applications. But once you go out there, the hope is that you will be able to apply what you learned, right, to see to what it is that you are going to face out there every day, let's see, right. So, let us move on out here. We were trying to, I guess, look at modeling how biological or biochemical oxygen demand is going to decay. First aspect is that when we say biochemical oxygen demand, what is it that we are referring to? We are referring to the organic matter, right, and we are indirectly measuring the organic matter that can be oxidized by microbes in the presence of oxygen, right. So, that is one thing that we need to keep in mind. So, when I say we are modeling BOD decay, we are more or less modeling the how organic matter decays in that experiment or in river or in the lake, right. So, that is something to keep in mind. And why are we concerned about that organic matter which can be measured by BOD? Because when I release this organic matter into the river, let us say, it is going to start decaying, meaning it is going to consume oxygen. So, oxygen content is going to decrease and decrease and decrease, and once the organic matter has been consumed, it is going to restart increasing again. So, this is the river water surface and this is the DO profile, let us see. If considerable organic matter is dumped here, so this organic matter is going to be degraded in the presence of oxygen by microbes. So, that is why you are going to have oxygen decrease in the river. So, the river is flowing in this direction. Yes, again that is one aspect. So, let us first understand how to model what is happening in this BOD bottle. So, there is no flow coming in, no flow going out, right. So, obviously it is a batch reactor, and we are going to try to measure the organics here and then try to apply it to the BOD measurement, let us see, right. So, let us move on and see what we have. So, obviously as we mentioned, control volume is the BOD bottle, and we are applying the mass balance on the organic content inside the bottle. Mass balance equation, no flow coming in, no flow going out, mass balance for the macroscopic scale, where the concentration of the compound in the control volume is the same, right. So, we have this rate of loss. How is it being lost? We know that it is being lost by reaction with microbes, let us see, right. So, again I guess we discussed this. So, let us not go into it in greater detail. So, pseudo first order loss. Why pseudo? Typically obviously what is it going to be depend upon? Certainly the oxygen concentration and microbial activity, certainly the oxygen concentration. So, it might be a true first order, not first order, pardon me, second order, but at most oxygen levels it is more or less pseudo first order, right. And we know that the oxygen should not decrease below 2 milligram per liter. That is when microbial activity is going to be affected. In that context, obviously first order loss, A going to products, right, or in this case since we are using L to indicate organic matter, L going to products. So, rate of reaction, which is also equal to rate of loss of L, is equal to the rate constant K times concentration of the reactant at time t. So, that is what we have. Again, you should not give a minus out here because we already have a minus out here, right. So, that is something to keep in mind. So, let us go forth and just apply, right. I guess this we discussed. So, this is the equation that we end up with, integrating, pretty straightforward. LT is equal to L naught. What is L naught? L naught is the initial organic content in the organic matter, or L naught is L at time is equal to 0 in the BOD bottle, right. T is the time at any particular point, let us say, right. And I guess we looked at this, but again what is BOD? BOD is biochemical oxygen demand, and the units are in terms of, or equivalents in terms of oxygen milligram per liter, let us say, right, oxygen consumed in milligrams per liter of water. Biochemical oxygen demand, let us say. So, let us say if the organic content initially was here, and then after some time this is the organic content, and if the units are in terms of or equivalent I guess in terms of oxygen, let us say oxygen equivalents, right, that is the right term. So, what is the oxygen demand? This is at time equal to 0 and this is at time equal to t. So, what is the oxygen demand? This is the oxygen demand and this is the BOD, let us see, at time t, right, at let us say time t1, and at time t2 obviously more BOD and BOD T2, let us see. Anyway, it is getting a bit cumbersome here. So, let me not look at that further. So, BOD at time t is nothing but the initial organic content minus the organic content present at time t, right. So, substituting this out here, we come up with this equation, right. And one aspect to note that is that if you put t equal to infinity or give run this test for a long period, what is the BOD that you are going to get? BOD is going to be equal to at when we give sufficient time, which we call BOD ultimate, is going to be equal to L naught, which is the initial organic content, right. So, that is something to keep in mind. BOD ultimate is the initial organic content or is equal to the initial organic content, and that is what I wanted to represent here. In Excel we got this done, or rather I got this done. So, loss of organics and the rate constant is 0.3 day inverse, note the units, and initial organic content, which is nothing but the ultimate BOD, is 200 milligram per liter. I just drew this line out here to represent that. Okay. What was the initial organic content? It was 200 milligram per liter, that is the one I took for fitting it into this model, let us say. And organic content remaining and BOD in units of milligrams per liter of oxygen. Keep in mind that even for organic content remaining, the units are equivalents in terms of milligrams per liter of oxygen. So, first LT, this is the organic content remaining. Initially at time equal to 0, it is going to obviously be equal to 200 milligram per liter. So, as time progresses, the organic content is being degraded by microbes in the presence of oxygen, let us say, right. So, that is what we have. So, at BOD 5, I guess let us say this, right, BOD 5 days, yes, this is what we are going to have, and if I run it for longer period, so 12 days. So, let us say if I run it for 20 days, it is all the organic content is going to be consumed. But what is BOD at time t, right? It is the oxygen demand, let us see, right, how much has been consumed, and this is what is remaining. If you remember, okay, LT is organic content at time t, right. So, I though want the difference, that is the BOD. So, right, if this is LT and this is going to be L naught minus LT, which is equal to the BOD at that particular value, and that is what we plotted out here. So, this is BOD, right. So, this is BOD. As you see, the BOD or oxygen demand is increasing with, or the oxygen demand, let us say, that we observed at increases with time, let us say, biochemical oxygen demand, let us say, right, which gives you an idea about the organic content that has been consumed. So, at 5 you see it is out here, and if I run the test for longer, most of it will be consumed. So, I will be able to estimate the organic oxygen demand at let us say 20 days or so, which is more or less typically going to be equal to 200 milligrams per liter. So, I guess that clears up the relevant aspects. Again, LT is the organic content left in the solution, but I want what has been consumed, right, biochemical oxygen demand, right, what is the oxygen demand if I let the system run for 5 days, let us say, and that is going to be equal to L naught minus LT, that is the organic content that has been consumed within time t. So, that is what we have, right. So, let us move on, and I guess a simple example out here, if BOD 5 of a waste is 102 milligram per liter and BOD 20, which we say is more or less equal to ultimate BOD, is 158 milligram per liter, what is the pseudo first order rate constant for the degradation of the organics, right. So, here we have BOD 5 at time t is equal to 102 milligram per liter, and BOD 20, which we say is the ultimate, is equal to 158 milligram per liter, right. So, again what is this? This is not LT, I was about to say that this was LT. So, this is L naught, which is more or less initial organic content present, right. That is what we have BOD ultimate, right. What is BOD ultimate? It is nothing but going to be equal to the initial organic content present. BOD ultimate means, if I give enough time for the BOD test to be run, what will be the total oxygen demand in that period. That will be equivalent to the initial organic content, and that is what I have here. And BOD at time t, BOD at time t is equal to obviously L naught minus LT, initial organic content minus organic content left at time t. So, that is equal to L naught into 1 minus e power minus kT. So, I have this value, and I know time period to be 5 days. So, I can calculate the rate constant. So, one unknown and so on and so forth, but typically this is not a good way, because when what do we say, when you are trying to capture the rate constant, obviously it is a rate constant small k, right. You want to have multiple what do we say sets of data and fit the model and get the rate constant that will minimize the sum of squared errors. So, this is the error, let us say, between the measured value and predicted value, right, measured value, predicted value, measured value, predicted value, and this is your model. So, that k, which will give you the least sum of squared errors, where each error is more or less nothing but the actual value or measured value minus the predicted value, right. Again, I should have drawn it in this way, I guess, fine. Okay, so, but here we are just using one data point, but here typically relatively more the better, and there is a limit obviously. So, here we are trying to approximate k by using one data point, that is what I was trying to emphasize here. So, let us move on, and what do we have here? Let us just see what we just discussed and what is k, okay, and so on. So, it is 0.21 day inverse, right. So, that is something for us to keep in mind. So, again biochemical oxygen demand, okay, similar to us humans, microbes also depend upon temperature. So, typically rate constant increases with temperature until a certain extent. Obviously, after that temperature increase is going to kill or going to adversely affect the bacteria. So, that is what we have here, we have empirical formulas. Again, you are not going to have to mug them up, they will be given in the exam. So, here empirical approach, again what do we have here? As temperature increases, again what I just mentioned, metabolism of microorganisms increases, thus the rate constant for degradation of organics also increases, but again until a threshold though. In general empirical approach, rate constant at temperature T, this is not time, at temperature T is equal to the rate constant at 20 degrees centigrade into theta to the power of T minus 20, and theta will have different values based on empirical what do we say observations, let us say, right. So, that is what we have, and example I guess rate constant blah blah is k, and it was supposed to be 0.2 day inverse at 20 centigrade, and what is the k if it increases to 25, and what is it if it decreases to 10. So, I think we had that right. What was that? K at 20 degrees was 0.20 into theta to the power of T minus 20, right. So, that is going to be your k at a particular temperature. I mean it is pretty straightforward. So, we can leave the calculations aside. Okay, so when theta is 25, not theta, temperature is 25, we see the increase in the rate constant, and when temperature is less, obviously a much more significant effect, right. We have a lower rate constant, but I believe I have a graph here, okay. So, what I did was, so this is the BOD again with ultimate at 200, BOD ultimate or initial organic content was 200 milligram per liter, or as you can see here, and then the 20 degrees with the rate constant at 20 degrees centigrade, you see this is the BOD profile, but if I increase it, yes, slight increase. But if I decrease it though, obviously, but again I did decrease it by 10 degrees centigrade here, but here increase by 5, you see the adverse effect is going to be relatively high. And this is one reason why, even though our wastewater treatment plants are relatively poorly maintained, our average temperatures are 20 or 25 degrees centigrade typically. That is why the system goes by or passes by, let us say. But as you see in colder temperatures and such, the rate constant is remarkably low, and that is why most of your microbial activity needs to be carefully monitored, right. So, that is something to keep in mind. Again, let us move on. So, obviously, I guess the inverse of what we discussed earlier. Earlier, we looked at BOD at a particular temperature at a particular time. So, that is equal to L naught at a particular temperature, not a particular temperature, right, and LT at a particular temperature, let us see. But here we are just looking at LT, and that is what you see. The organic content left is higher when we are running the BOD test at lower temperature, because microbes can't degrade the let us say at 5 days. You see that you have more organic content left. Let us say we are looking at 5 days. So, you have more organic content left at low temperature, because microbes can't thrive as well at low temperatures, right. And obviously, at high temperatures it is going to be relatively better, or the removal rate is going to be relatively better. So, that is what we have here, simple Excel calculations. So, but here until now we have been looking at dumping a waste, not dumping a waste, pardon me, modeling the organic content in the BOD bottle, which is a batch reactor. But again, the whole point is to understand what happens, let us say if I discharge waste from an industry into a river, and here in and around Roorkee and such, where we are in the Ganga basin, let us say, typical issues are with respect to distilleries, and they are required for preparation of alcohol too, right. Alcohol again, which is also used in pharmaceutical industries also, right, not just for human consumption, and also textile industries. These are the major issues, and they are unable to treat the waste well. Typically BOD here might be 1 lakh, okay. Textile too may not as high as this, but issue is with respect to color, compounds which cause color, which typically cannot be degraded by microbes. So, they dump the waste treated, typically hopefully partially treated and untreated waste into Ganga, and we have issues, let us see, right. If not into Ganga, the other tributaries or chains, let us say. So, here we want to understand what happens to river water quality during, let us say, mass bathing festivals. Let us say people throw flowers and such, looks good on camera, but flower again organic content, let us say, right. I will not make an effort to draw a flower here. So, again let us say if I dump this flower into river, again that is organic content, and that has to be degraded, right, and that is going to consume the DO, affect aquatic life. So, do not throw stuff into the river, right. Again, and what else during bathing festivals and such, where you will also have not just pathogens, but considerable organic content released into the relevant rivers or surface water bodies. And as we mentioned earlier, downstream of Delhi, remarkably highly polluted streams join river Yamuna. It is pretty much dead ecologically. And where will the river quality with respect to DO be acceptable? Let us say if I want to know where the DO will be 4 ppm again, how do I do that, let us say, right. There are different reasons for it. You want to bathe in the river, you want to start what do we say, a fishery out there or aquaculture, or you just want to buy a house where you can have drinking water of acceptable quality. Anyway, different reasons. So, how do I do that, let us see, right. So, here keep in mind that we are talking about a river, or let us say Ganga canal, and I am dumping my waste out here. I believe looked at this example quite often, Haridwar, Roorkee, right, and so on and so forth. And we saw that here there are two aspects. One is advection, which leads to dilution of your relevant compound if it is not a constant source. But again, transport along with fluid which is flowing in one particular direction, or fluid which has a net fluid flow in one direction, advection. And obviously, you are going to also have degradation by your microbes, let us say. So, how do I take that into account? So, this as you can see is very much similar to the plug flow reactor, right. This is one of the ideal case reactors that we discussed. So, let us see what else we have here. I want to model the effect of dumping. So, model the effect of dumping of oxygen demanding waste into a river, right. So, how do I do that, or let us understand what is going to happen. Let us say if we have relatively pristine quality water out here with 8 ppm high dissolved oxygen. So, this is my point 0, let us say, okay. This is upstream of Haridwar, let us say. And at Haridwar, let us say where we have the industrial zone, we have considerable waste being dumped into it here, okay, dumped into the stream here, and obviously what is going to happen, there will be initially some decrease, but at that point not a lot of decrease in dissolved oxygen, because it is instantaneous mixing here, but BOD is high, but the microbes have not had the time to degrade it. But as we move downstream towards, let us say this is Roorkee, right, what is going to happen? Along this, as the organic content, let us say, which has been dumped here is going along, you now have the organic content spending more time in your reactor, right. The reactor here is, this is my reactor here, right. So, that is my reactor, and what do I have here? I have mass coming in, or fluid flow coming in, and fluid flow going out, right. So, how do I understand this again? So, what is happening to the BOD here? Biochemical oxygen demand or organic content is relatively high. Suddenly it is very high, the organic content here, and why is that? Because the waste has been dumped, and slowly but surely it is going to be degraded. That is why the organic content is decreasing, right, until it reaches relatively low values again by the time, let us say, it hopefully by the time it reaches Roorkee. But in the meantime, what is happening? How is this organic content being degraded, right? Here the BOD is very high and here the BOD is less. How is it being degraded? Right, it is being degraded by the microbes in the presence of oxygen. The critical aspect is oxygen, let us say, right, oxygen. So, this is oxygen out here, and as we see, it is decreasing at a pretty fast rate and it reaches a minimum. So, that is why you have fewer varieties of fish and anaerobic conditions, which typically lead to, what do we say, conditions that let pathogens thrive, pathogens. So, decomposition zone and then septic zone, right, and from this point on, what is happening, again your DO levels are starting to increase and they will take quite some time to reach the relevant levels that were there before the waste was dumped, right. Again, what is happening here with respect to this, the rate of loss of oxygen is greater than the rate of, what can I say, not gaining, reaeration, let us say, rate of formation of oxygen, let us use the term formation. So, in this zone, rate of loss of oxygen is greater than rate of formation of oxygen, and in this zone obviously the rate of formation of oxygen is greater than rate of loss of oxygen. So, we know how this oxygen is being lost. How is it being lost? When this organic content is being degraded by the microbes. But how is it being formed? Typically you will have aquatic life out here, right, and typically algae and such, and you will have photosynthesis and oxygen will be given out, let us say, right, and this is usually a pretty good source. But let us say in fast flowing river waters and such, we might or we will not have this from photosynthesis, lakes and such, yes. So, but typically you have oxygen in the atmosphere, oxygen in the gaseous phase. We have Henry's law. We know that given enough time it is going to try to achieve equilibrium, and it is going to try to achieve equilibrium, let us say, but typically it will not. But here, depending upon the turbulent conditions on top of this particular canal or river, you are going to have transfer of oxygen from the atmosphere into the what is this now, into the river, right. So, that is how, when we say rate of formation of oxygen, that is what we are referring to, it is the rate of reaeration. When I say rate of formation, it is the rate of reaeration, right. So, that is something to keep in mind. So, let us move on and see what else we have here. So, just a similar schematic out here. So, what is this now? This is the river flowing here, and the pollution is being dumped in where the point is x space, x equal to 0 and time is 0, that is what we are understanding out here. And keep in mind here that when we say time, it is misleading. So, actually it is theta, which is hydraulic retention time, let us see. For example, you can't say now that you have you started at Haridwar and you travel from Haridwar to Roorkee, right, and say that the water has taken such time or such, let us say, and we are more or less changing the space, let us see, right. Okay, I guess the better way to explain is, let us say I take a sample here and then I rush from here to here, from Haridwar to Roorkee, and I take a sample at Roorkee, and you can't say that I am measuring the effect of time. You are not measuring the effect of time per se, you are measuring the effect of change in concentration with x or change in concentration with space, right. So, that is what you are measuring. So, this x though when we divide by u, right, that is hydraulic retention time, the time that the reactor has spent in the system. If you say you want to check the change in concentration with time, you should just sit at Haridwar and check it at different times, 8 a.m. to noon, right, 4 p.m. and so on and so forth. You have to keep the space constant and check it with respect to time. So, that is one common mistake, but again I guess let us move on. So, here we are dumping pollution, right. Initial deficit means let us say saturation DO saturation is this and minus current DO, this is the deficit. Initial deficit is DO, right, and what is that? If this is the DO saturation level and this is the initial DO, this is the deficit, right. And what is happening to the DO? Keep in mind y axis is dissolved oxygen, it is decreasing. Why is it decreasing now? Because here you are having organics dumped in, and with as let us say the compound travels along your reactor or spends more time in your reactor, the microbes have had more time to what do we say degrade the relevant compounds and use up oxygen. So, that is why oxygen is decreasing, and we have the critical point xc or theta c, right, x critical or theta c, where we have the critical point, and then again oxygen starts increasing, right. So, that is the hope, and the key aspect is to design it such that the critical deficit, this will be the critical deficit or the maximum deficit maximum or critical deficit should not be what we say such that your DO levels are less than 2 or 3, right. That is the whole aspect of what we are going to discuss, let us see. So, here we already discussed plug flow reactors in detail earlier. So, here we are going to just look at it again. So, again here keep in mind that it is changing with distance and it is not with respect to time. So, I should say theta equal to 0, theta 1, theta 2 and theta 3, and distance is x0, x1, x2 and x3, right. I know it is a common mistake and a petty mistake, but I still would like to point it out. So, key aspect to note is that the concentration of the compound changes based on the amount of time it spends in the river. So, that is theta, which is called the hydraulic retention time. It does not just change with time, it changes with the amount of time that it spends in the reactor or the distance it travels, let us say, right. So, here let us say again I think that is pretty self explanatory, right. Thus, the concentration of the compound changes with distance along the river, right. We discussed this. And let us move on. So, the plug flow reactor ideal case, river also yes, there is a plug flow, right, the plug is flowing along plug flow, let us say, right, plug flow reactor, that is what we are going to have. Again we are going to assume that it behaves as a plug flow reactor, but typically it is a good enough assumption. So, mass balance on the river and so on and so forth. Keep in mind that we looked at the fundamental mass balance equation dc by dt plus u dc by dx, assuming there is no diffusion and no other sources or sinks, plus or minus sources or sinks, rate of formation minus rate of loss, right. We are assuming that the flow is only in one direction, which is x direction. So, this is for microscopic scale too, and you can apply that here, right. And typically why can't I apply this equation as it is to this whole reactor now? Why is it? Because as you see here the concentration is changing with x, but here we do not have that, we just have it changing with time meaning at a particular point in space only. And also keep in mind that when you say you take the reactor or control volume, define the control volume, you have to see to it that the concentration within your entire system is the same, right. That is the whole point out here when you are trying to integrate to. So, obviously you can't take this to be a continuously stirred reactor, or you can't apply this macroscopic scale equation as it is. You can either apply this microscopic and universally applicable mass balance equation, or you can transform this, and looks like I am out of time. So, I guess we will continue this in the next session, and as usual thank you for your patience.